This is potassium ferrocyanide's molecular structure. As you can see, it is an ionic compound which consists of four potassium cations and one ferrocyanide anion. This is the digital model of potassium ferrocyanide. I will showcase the arrangement of atoms and the type of chemical bonding present. This compound consists of an octahedral ferrocyanide center cross-linked with potassium ions that are bound to the cyanide ligands. Let's look at the ferrocyanide ion first. The nitrogen, each nitrogen in this ferrocyanide ion is covalently bonded to a carbon, in which they form three covalent bonds between them. And then each carbon in this ferrocyanide ion forms one covalent bond with the central iron 2 atom. So the overall structure of ferrocyanide is octahedral in shape. And then we have four potassium ions that are cross-linked to this central ferrocyanide ion. And each of this potassium ion forms an ionic bond with this ferrocyanide anion. The atoms present in potassium ferrocyanide are potassium, iron 2, nitrogen, and carbon. Now, for each of these atoms present in potassium ferrocyanide, I will present its details about their atomic structure, including electron configuration and valence electrons. Potassium has an atomic structure of one central nucleus and four shells. The valence shell of potassium only has one valence electron. Its electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, and 4s1. 4s1 is underlined because it shows that it is the valence electron, which is 1. Next, iron has an atomic structure of a central nucleus and four shells. Its electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. 4s2 and 3d6 is underlined to show that it is iron's 8 valence electrons. However, only 2 valence electrons are involved in the bonding of in potassium ferrocyanide. Furthermore, nitrogen has an atomic structure of a central nucleus and only two shells. Nitrogen's electron configuration is 1s2, 2s2, 2p3. 2p3 is underlined indicating that it has three valence electrons. Lastly, carbon, similar to nitrogen, has an atomic structure of a central nucleus and only two shells. Carbon's electron configuration is 1s2, 2s2, 2p2. The underlined 2p2 shows that carbon has two valence electrons. I will explain how the atoms in potassium ferrocyanide relate to their positions in the periodic table. So, I have shown all four atoms in potassium ferrocyanide here along with their electron configuration, as well as the underlying valence electrons. Let's look at potassium first. The valence electron is in the 4s orbital. So, potassium is located in the S block. More specifically, potassium is in the first group, group 1, which is alkali metals. Next is carbon. The two valence electrons in carbon is located in the 2p orbital, which makes it an element in the p block. Similarly, nitrogen, which has three electrons in the 2p orbital, is an element of the p block too. Carbon and nitrogen is located in group 14 and group 15 respectively, which is non-metals. Last but not least, iron has 8 valence electrons, in which 6 are located in the 3d orbital and two valence electrons are located in the 4s orbital. Since its valence electrons are located in the 4s and 3d orbital, iron is located in the d block. Iron is located in the d block, and it is a transition metal.
On to the next part, we will discuss about trends or patterns in the properties of the atoms within potassium ferrocyanide based on their location in the periodic table. First, let's look at the potassium element. Potassium are located at group 1 and period 4 in the periodic table. Based on the location, potassium is a metal, and we can see that group 1 is an alkali metal. As we move on to group 1, the trends for group 1 are the atomic radius increases, the ionic radius increases, ionization energy decreases, electron affinity decreases, electron negativity decreases, both the melting and boiling points decreases, metallic character increases, and the oxides becomes more basic. While across period 4, the trends are the atomic radius decreases, ionization energy increases, electron affinity increases, and electronegativity increases. Besides that, what we can see from potassium is it has a low first ionization energy since the atomic size increased down the group. Because of that, the attraction between valence electron and nucleus become weaker. Therefore, the valence electron is easily removed from the atom when enough energy is provided. And next, we will see the trends of iron atom, which is located at group N and period 4. Iron is one of the transition metals based on its location. It is located at D block. Transition metals are defined as those elements that have partially filled d orbitals. The properties include have large charge or radius ratio, are hard and have high densities, have high melting and boiling point, show variable oxidation states, can form colored ions and compounds, can form stable complexes, can form complex ions, and can function as catalysts. Transition metals demonstrate a wide range of chemical behavior. For example, ions of the D block elements such as chromium 3 ion, iron 3 ion, and cobalt 2 ion can form colorful hydrated ions that are stable in water. However, ions in the bridge just below this, which is molybdenum 3 ion, radium 3 ion, and iridium 2 ion, are unstable and react readily with oxygen from the air. Instead, scandium and zinc do not count as transition metals even though they are members of the D block because of both do not show characteristics of transition metals. So we have seen potassium and iron. Now let's take a look at nitrogen. Nitrogen is located at group 15 and period 2 in periodic table. Nitrogen is also a non-metal. Moving down group 15, the trends are the atomic radius increases, the ionic radius increases, ionization energy decreases, electron affinity decreases, electron negativity decreases, metallic character increases, the oxides becomes more basic, and the melting point first increase from nitrogen to arsenic and then decrease to bismuth. While across period 2, the trends are the atomic radius decreases, the ionization energy increases, the electron affinity increases, and the electronegativity increases. In general, the first ionization energy increased across the period too. However, the increase is not uniform. It is expected that the first ionization of boron to be larger than beryllium and oxygen to be larger than nitrogen due to their small size. However, the outer electron in beryllium is in sublevel which is in a stable 2s2 configuration that require high energy to remove it, then to remove an outer electron from boron where the electron is in the p sublevel. For oxygen and nitrogen, the two p electrons in nitrogen are all unpaired. In oxygen, two of the three p electrons are paired in the same p orbital. There is some repulsion between paired electrons in the same sublevel. This reduces the force of their attraction to the nucleus, so less energy is needed to remove one of these paired electrons than is needed to remove an unpaired electron from nitrogen. See the trends or patterns of carbon atoms. The carbon atoms located at group 14 and period 2 in periodic table. Carbon is a non-metal. Moving down to group 14, the trends are the atomic radius increases, the ionic radius increases, ionization energy decreases, electron affinity decreases, Electronegativity decreases and metallic characteristic increases. We can see that carbon and silicon is a nonmetal, germanium and tin is a metalloid, lead and flerobium is a metal. While across period 2, the atomic radius decreases, ionization energy increases, electron affinity increases, and electronegativity increases. Across period 2, the melting point increases from group 1 to group 14 because the elements have joint structure, metallic and then covalent. The melting point decreases from group 14 to 15 because the structure changes to simple molecular structure with weak van der Waals forces. This is also because as we move across the period, we are adding more valence electrons to the element. Now, I'd like to discuss about the types of chemical bonds present in potassium ferrocyanide. Potassium ferrocyanide consists of ionic bonds and covalent bonds. First, ionic bonds present between potassium ion and the ferrocyanide ion. Second, covalent bonds present in the cyanide ligands between carbon and nitrogen. Lastly, coordinate covalent bonds present between iron 2 ion and cyanide ion. Next, we will see the bonding influences. There are ionic bonds and covalent bonds in potassium ferrocyanide. Let's discuss about how the bonding influences the molecule's properties and behavior. First, ionic bonds influence. Because of ionic bonds, potassium ferrocyanide is soluble in water. The ionic bonds in the molecule makes the substance highly soluble in water. Second, covalent bonds influences. Covalent bonds influences are the potassium ferrocyanide can has high stability. Strong covalent bonds and coordinate bonds within the ferrocyanide anion are the one of the contribute to its stability. Besides that, covalent bonds allows the potassium ferrocyanide to interact with many substances. Lastly, covalent bonds also produce a non-toxic substances. Although the molecules consist of cyanide ions, that is toxic, they are bound more tightly to the ion atom and makes potassium ferrocyanide less toxic.
Okay, so next let us continue with its real world applications. And firstly, it is mainly used as an indicating agent for table salt and road salt. This is to prevent it from clumping and to ensure the product to remain dry. So with this, it is easier for the product to be produced and packaged, which is the table salt and road salt. So then it is also used in the separation of copper in molybdenum ore. Other than that, it is also used in the purification of tin, which is one of the major process in the industry. And the third one is it can also act as a plant fertilizer. So prior to 1900s, before the invention of casting process, it was most important source of metal cyanides, which is potassium cyanides, and it was made by composing the potassium ferrocyanide. Okay, as for the last fundamental point, which is how its properties contributes to its function in many field and uses. Primarily, in daily life, it is chemically stable and has a low level of toxicity. So with this, it is safe for them to be used for food preparation and preservation. So other than as a anti-caking agent, it can be used to produce wine by removing the heavy metals in it, and it is also used to preserve fruits by fermentation. Next, as for the industrial uses, it can act as a corrosion inhibitor. So it is utilized in chemical and pharmaceutical industry as well as electroplating industry. And as it has a precipitation properties, it is also useful in identification and determination of iron in iron ore. As for the last point is which is how is it useful in the research field. So firstly, it has a property to react with the ferrometry and produces a Prussian blue color. And this serves as an indicator in various titrations and chemical analysis. Next, it also has a redox properties. So with this, it can be used to cleave Excel and producing a bright blue visualization. This is our references. So these are some of our references, and most of them are actually from my label textbooks. These are also our references that we use, and that's all from us. Thank you.